In Lecture 10 of our General Chemistry module, we are going to talk about acids and bases. Starting first with some definitions. Acids and bases in particular have a lot of different definitions, 3 in particular. We'll go into all 3 of them. The Arrhenius definition states that acids are what donate H+, or make H+, and bases make OH-. This is in reference to water, but obviously this definition doesn't quite cover all the types of acids. There are many acids and bases that don't have H+ or OH, so how do we define those? Well, that's where the other 2 come into play. The Bronsted-Lowry definition states that acids are proton donors and bases are proton acceptors. Lewis' definition states that acids are electron pair acceptors and electron pair donors. Keep these definitions straight. You're often going to be tested on what type of compound something is, and the answer choices are going to be some amalgamation of Bronsted-Lowry base acid, Lewis acid base, or Arrhenius acid base definitions. An amphoteric species is noted as something that behaves as both an acid or a base depending on the system. For the MCAT, oftentimes water is going to be the most common example of an amphoteric species. Why is this? It's because water can also act as both depending on what the other compounds in the system are. Now that we've gone into some fundamental definitions of acids and bases, let's go into some properties of these compounds. The most important thing to note with acids and bases is pH and pOH. This is based on Kw, which is the dissociation of water. The value is noted as 10 to the minus 14th. What you also need to note is that if you were to take your pH and pOH, they do have to add up to 14. pH is noted as the negative log of H+, whereas pOH is noted as the negative log of OH-. If you multiply these together, you are going to have to equal 10 to the minus 14. Therefore, if you have a pH, you can interchangeably change to pOH and vice versa. One thing to note though is that sometimes the proton is going to be represented as H3O+. But this is identical. These are the same thing, so don't get confused by that. When it comes to pH, you're often going to have to do a lot of logarithmic functions, which requires some estimation because you're not going to have a calculator on test day. Below is an approximation system that more or less works. Here's the breakdown of it. If you look, your p-value, your pH or pOH value is going to be approximately whatever m is, whatever the exponent is, minus 0.n, which is what that scientific notation base is. This will generally get your calculations down on the MCAT, so I strongly encourage you have this memorized. This brings us into Ka and Kb, which are acid dissociation constant and base dissociation constant respectively. Here are the 2 representations of it. Take note that Ka times Kb has to equal Kw. This is true for either case, so again, you can use Kw to exchange between the 2. Note that a strong acid is one that completely dissociates, and a strong base is the same as well. A weak acid or a weak base is one that does not completely dissociate, so keep that in mind. Something that we do have to discuss also is what it means to be polyvalent. So, polyvalence is simply noted as a species that can either act as of acid or base multiple times. So an example of this would be if we were to do for acids, if we were to use H2SO4 as an example. This is considered polyvalent because sulfuric acid can donate 2 protons, like so. Step 1 and step 2, respectively. Because of this, sulfuric acid is commonly considered polyvalent. When we're talking about acids and bases, we need to also discuss titrations and buffers, which are often the ways that we use acids and bases in science to quantify values. There are several points of interest when you look at a titration curve, which you will have to read on an MCAT. The equivalence point is noted as the acid concentration and base concentration. This is where the 2 are equivalent. Below is an example of a titration curve, and the equivalence point is labeled for you. For a strong acid and base, the pH is going to be 7 at this point. For a weak acid and strong base, it's going to be more than 7, and it's going to be less than 7 for the other case. The endpoint is when the indicator reaches its final color, and the endpoint on a graph like so, I'll use a different color so you can see it better. The endpoint is going to be represented at this juncture right there. This is when the indicator reaches its final color. Usually it's going to be pink, and I'm sure you've seen that in your Gen Chem labs. One thing I would like to note though is that half equivalence point right here is going to be the pKa value. So that might be helpful when you're looking at these graphs on test day. The last thing we're going to talk about is the Henderson-Hasselbalch equation, which is used to account for buffers. What is a buffer? A buffer is a mixture of a weak acid and its salt, or a mixture of a weak base and its salt. A buffer is going to resist the change to pH or pOH respectively. The equations for the two are listed below. In the previous slide, I talked about how you can find pKa from a graph. You can also do this for pKb, but it depends on the titration graph. Take note of how this applies. You will be asked to do buffer calculations on the test. Remember that a good buffer is one that is going to resist change. A bad one is one that's going to be less capable of doing so. That'll cover our acids and base discussion. As you can see, there's a lot of different definitions of acids and bases and a lot of ways to apply them. Make sure you take note of these applications and you're sure to do well on test day. We'll see you in the next lecture.